Hi, this is Dr. Patrick again. Now we are going to learn how to create and use probability distributions because knowing the shape, central tendency, and variability of a probability distribution will actually enable you to make decisions in inferential statistics. So we're going to look at, two types of random variables. We're going to look at discrete probability distributions, and we're also going to talk about binomial distributions. So let's get started. The outcome of a probability experiment is often a count or a measure, and when this occurs, the outcome is called a random variable. So a random variable, let's just say x, represents some sort of numerical value associated with each outcome of a probability experiment. And the word random indicates that x is determined by some sort of chance. And there are two types of random variables that we encounter. We have discrete and we also have continuous. A random variable is discrete if it has a finite or a countable number of possible outcomes that can be listed. A random variable is continuous if it has an uncountable number of possible outcomes. It's represented by an interval on the number line. So if a random variable is discrete, you can list the possible values that it can assume. However, it is impossible to list all values for a continuous random variable. So, a discrete random variable, think about rolling of a die, right? There's only 6 sides. Some sort of continuous random variable. Here in Texas, you blink, you never know what the temperature is going to be. So it's a finite, infinite number of possibilities, right? Versus rolling a die, you only have 6 sides. So it's finite. After the uncertainty is resolved, we can observe the results or realized value for a random variable. And before the uncertainty is resolved, all we can do is study the likelihood or probability of each possible outcome. And I'm going to use the die because that's one everyone is probably familiar with. The probability distribution of a discrete random variable is expressed as a table, a graph, or formula that gives a probability associated with each possible value that the variable can assume. And it's notated, or the notation is x is the value of the random variable, and p of x, that's the value's associated probability. And there are certain properties. For any value x of the random variable, the probability of x is greater than or equal to 0. The probabilities of all the events in the sample space must sum to 1. That is, the summation of the probability of x must equal to 1. And let's look at this. So think about tossing a coin. There's only heads and tails, right? You have a 50-50 chance. So if you add the probability of, tossing a head, which a heads, that would be 0.5, and the probability of, flipping to tail, that's 50%. That summation, the total is going to be 1. And the same thing is for rolling a die. There's only 6 sides, so you've got a 1 out of 6 chance of rolling a 1. Same for 2, 3, 4, 5, and 6. As you can see, the summation is equal to 1. Okay, so I like Zara, and I want to talk about Zara t-shirts, so I chose this example. Let's say you are the manager of one of the Zara stores in Texas, and based on the past sales data, you expect demand as the following, right? So of selling 20 shirts, the probability is going to be 15%, 0.15, 30, 0.25, 40, 0.25, 50, 0.25, and then selling 60, t-shirts, it's 10%. So let's look at different probabilities of demand. I also added a cumulative probability here And so the cumulative distribution function table here, what it says is that for each value of x, which is 20, 30, 40, 50, and 60, the probability of a result will be less than or equal to x. So, less than or equal to is often written at most or no more than. All these phrases have the same meaning. So let's look at a few examples. So what is the probability that the demand for t-shirts is going to be exactly 50? Well, I'm going to come down here to where x is exactly 50. So my demand for that is going to be 0.25. What about if the demand is less than or equal to? These are very important words. I want to know if the probability of x is going to be less than or equal to 30. So guess what? I'm going to include 30 in that. So what I'm going to look at is, since I want to know what the demand is, I'm going to go over here to 30 and I'm going to add, I want to know for 20 and also for 30. So 0.15 plus 0.25, that gives me 0.40. What about if the demand is less than 50? Okay, keyword here, the equal is not in this question. So I want to know what the probability of x is less than 50. So what I'm looking for is a probability of x being less than or equal to 40. So all I'm going to do, guess what, is add up all of these, and that gives me 0.65. All right. So what about if the probability that the demand is at least 50? So that's going to be that the probability of x is going to be greater than or equal to 50. So I've got to include 50 and 60 here, right? So 0.25 plus 0.10, that's 0.35. What about if the demand is greater than 40? Once again, equal to is not in that question. So I'm looking for the probability of x is greater than 40, which is also equal to the probability of x greater than or equal to 50. So I've got to take 0.25 plus 0.10, that gives me 0.35. All right, now I want to talk about the expected value of a discrete random variable. So the mean or the expected value of a discrete random variable x is mu to the x equals the summation, all of x, right, times probability of x. So in the Zara example, what we're going to find out is that the expected demand is going to be 39. So I have my tables here. I have x, the probability of x, and so if I want to find the expected value or the expected demand, I'm going to take my x, multiply it times the probability of x for each one of these, and then I'm going to sum it up right here. So I get 39. All right, so now let's talk about how we find the variance and standard deviation. So the variance of a discrete random variable is, the summation of x minus mu squared times the probability of x. So the variance is the average of the squared deviations of the difference values of the random variable from the expected value. And the standard deviation is the square root of the variance. That's all it is. And you want to recall that the variance and standard deviation measure the spread. It's that dispersion of the values of the random variable from their expected value. And here's the chart that I put together for you. As you can see, I have, once again, in the Zara example, I have x, the probability of x. Remember, this has to total 1. We find the expected value right here, which is 39, which we already did. So now we want to find the variance and standard deviation. So the next thing I want to find is my x minus my mu squared, right? So what I'm going to do is I'm going to take x minus my mu. I'm going to square it. That's it. That's why we have to find the mu, which is 39. And then what I'm going to do is I'm going to multiply that by the probability of x and then add all of that up. And this is my variance right here is 149. And then Standard deviation is very simple. All you're going to do is find the square root of the variance. Okay, so now let's talk about binomial distribution. So, by listing the possible values of x with the corresponding probability of each, you can actually construct a binomial probability distribution. The binomial probability distribution is associated with a multiple-step experiment that we actually call the binomial experiment. And so, a binomial experiment actually satisfies certain conditions. The experiment is repeated for a fixed number. We always call n number of independent trials. There are only 2 possible outcomes for each trial. Each outcome can be classified as a success or a failure. The probability of a success must remain constant for each trial. And the random variable x actually counts the number of successful trials out of those n trials. So the parameters of a binomial distribution are n and p. So you use binomial when it is the exact probability of something. So, the probability of exactly x successes in n trials is what we are trying to find. So, in a binomial experiment, our interest is in the number of successes occurring in the n trial. So if we let x denote whatever the number of successes occurring in the n trials, we can actually see that x can assume the values of, it could be 0, 1, 2, 3, tossing a coin, a true or false question, because the number of values is finite, So let's just say I was thinking about once again, binomial probability distribution. The bi up here, that means 2. You've got 2 possible outcomes. Distribution means success or failure. Once again, it also has a fixed number of outcomes or has a set number of trials. Let's just say if I am playing basketball and I make it to the free throw line. So I have my chances of trials is how many shots, I actually hope to make. So my n would be 3. That's the number of trials. My x, that would be the number of successes, which is 2, right? So, and let's look at an example. Let's look at some shapes of a binomial distribution. So the shape of a binomial distribution, once again, it depends upon n and p. If p is too small, the distribution actually tends to be skewed to the right. If p is too close to 0.5, the distribution is symmetrical, which is this nice bell curve. If p is too large, the distribution tends to be skewed to the left, as you can see. All right, let's look at this example, a commuter airline. Let's suppose that you are a manager at a commuter airline. From the past data, the probability that a customer who buys a ticket will show up is 70%, and the capacity of the plane is 10 seats. So you just sold all the 10 tickets and want to know how many customers will show up. Well, so our experiment consists of, once again, n identical trials. So n is going to be our 10 customers or our tickets. Each trial results in either a success or a failure. They're either going to show up or not show up. And the probability of success, p, is going to be constant from trial to trial. And that probability of failure that we look for is 1 minus p, and is constant from trial to trial. So our p is going to be 0.7. 1 minus p is equal to 0.3. So our trials are independent. Yes, it checks all the boxes. So let's look. What is the probability that all the customers will show up? So I want to know the probability of where x equals all of my 10 customers are going to show up. So that equals 0.7 to the 10th. There you go. What is the probability that 9 customers will show up? We're looking for the number of ways to get 9 successes and 1 failures in 10 trials. So And here we go, the chance of getting 9 successes and 1 failure in a particular arrangement. And this is what the formula looks like, the binomial distribution, the probability in the binomial distribution. And I'm sure in your handy dandy Excel files, it is very easy to kind of plug and play for this one.